Corey Bauer, Simulation Manager with GoEngineer, and we're going to look at the analysis of welded structures.
First thing we're going to look at is some stress and vibration calculations or analysis on a welded structure. Then we're going to look at one where we are lifting the welded structure, in this case by 4 corners, with slings. And then the last thing we're going to look at is a detailed look at the actual weld in one joint or one corner of the frame. Okay. So the first thing we're going to look at is, basic stress analysis and some vibration analysis on a welded skid like this. So this example is something where we have a diesel engine, we've got a fuel tank next to it, and then we've got some kind of pump. And this particular one is designed to where it's just picked up with a forklift. So it's got some channels in there for the forks to slide in and pick it up. Okay. So the first thing we're going to do is just an analysis whether it can hold the weight, and then we're going to look at as the engine and pump are running, we're going to look at a vibration analysis. Okay. So for this, we're going to not look at the entire assembly. We're going to go to just the framework. Okay. So this particular framework was created in the weldment environment of SOLIDWORks. Okay. So what that means is everything starts a skeleton or basically a stick figure of the structure. Okay, so there's our basic layout. From there, we start to go through, and piece by piece, we define what type of beam or channel or square tubing or rectangular tubing that we want on there. So there's the main rails, and we've got some of the corners of the skid. We can do some mirroring. And then we just have to trim everything because the way the sketches were done, some of those members were overlapping. And then we just added the forklift channels and then the channels to mount the engine, the fuel tank, and the pump onto. Okay. Now, the nice thing about using those weldments inside of SOLIDWORKS is when we go into the analysis of that, it automatically creates those as a beam mesh for us. Okay? So if you haven't done a beam mesh, one thing you're going to notice is we've got some purple spheres, and then we've got some kind of goldish or green spheres. Okay? Those are called joints. So everywhere, every place on the model where 2 or more structural members come together, it creates a joint. So the joint is what attaches or connects our beam elements together. So a purple sphere is just showing that we've got 2 or more members coming together. The few that are the green or the yellowish sphere, that just means it's the end of a member that does not have another one connected. Okay. So the software automatically does that meshing of the beams for us. Okay. So if we show that mesh, you can see the segments or the elements as it runs down the beam. Okay. Now, if you have done beam analysis in earlier versions of SOLIDWORKS, you might recognize it as more of just a pipe or a round piece. Okay. Even though it used to display only as those round pipes or bars, okay, the software actually took the cross-section into account. Okay. In the last couple of years, they added just the rendering option to actually show it as the beam that you've defined. Okay, so that's a little bit nicer for visualization. Okay, so the question came up of what about creating a frame that wasn't done with weldments? Okay, great question. So we have two options on that. The first one is it will default to solid elements, but all you have to do is right-click on that item. And because these are beams, it says treat as solid, but if it was the other way, it would say treat as beam. Okay, so any solid can be turned into a beam. Okay, so that's how you would handle non-welded structures. Okay. So another next difference is when we get into our fixtures, first thing we're going to notice is the lift is a bit smaller on what you can do with beams. Okay, so you can have fixed geometry, you can have a movable, and then you can have use reference geometry. So it's much more limited, and the reason for that is if you look at what's available to select, we can only select joints for our fixtures. Okay, so in this case, because we are mimicking this structure getting picked up by the forklift, we are fixing the joint at the end of each forklift channel. Okay. When we get into our loads, we will also see that there's different on what we can select. So loads can be added to joints, just like fixtures, but it does have one more addition where we can apply the load to an entire beam. So that's what we've done because we've taken the engine out, we've taken the fuel tank out, and we've taken the pump out, we're just replacing them with a force. So we are taking two channels that the engine was setting on, applying it to the entire beam, and it's going to be 1,000 pounds total. Okay. So that is replacing the engine. On the fuel tank, on the entire beam, so the square channel and the rectangular channel, and it's also 1,000 pounds, representing the full fuel tank. Okay. On the pump, we are applying it to the entire beam, and that's going to be 2,000 pounds. Okay. So that's representing the pump. When we create the mesh, notice there was no place to choose the size. Okay, when it's a beam mesh only, the size is automatically and without control set by the software. Okay, because it is a beam mesh, it solves extremely quickly as well. Okay. So when we take a look at the stress plot options, okay, we're going to see a much different list than we would for a solid element. Okay, so nowhere do we have von Mises stress or principal stress, stress in the X, Y, or Z, or I should say the X, Y, or Z components of stress. Okay, we have results that more correspond to hand calculations. So we have the axial stress, we have the bending stress in direction 1 or 2. We have axial and bending combined, which is kind of a worst case. We've got torsional, and then we've got shear in direction 1 and direction 2. Okay. So we're going to look at axial and bending together. So again, that's kind of like a worst case stress value. Okay. So we can see that we have about 2,800 PSI for our stress. Now the material that we chose is plain carbon steel that has a yield strength of about 32,000. Okay. So that gives us a factor of safety in excess of 10x. Okay. So this structure can easily handle the 4,000 total pounds that we placed on it. Okay. If we take a look at the displacement, we're looking at 41 thousandths of an inch. Okay. Just like any plot, we can look at the automatic scaled or true scale. So here is the exaggerated, which makes it nice for the animation. Okay. So we can see the structure deforms just as we would expect if we were picking it up with a forklift by the channels. Okay. Now, if this structure just had weight on it, we'd probably be done with our analysis. But the fact is it's got an engine running and it's got a pump rotating. Okay? So that means we need to do a little bit further. So the next thing we want to do is calculate the natural frequency of this structure. Okay? The setup for the natural frequency analysis is identical to linear static. So we can take our fixtures, we can take our loads out of our linear static analysis, and we can copy them over. Okay, a couple of ways that we can do that. Going back to our linear static analysis, we could just right-click on the force, go down to the bottom of the menu, copy that, come back to frequency, paste it in. Okay. Another option is we can go back to the linear static analysis. We can drag the force onto the frequency analysis tab, and that copies it over. Okay. So in a typical analysis, you're always going to do your linear static stress analysis first. So you're going to have pretty much your entire setup already there that just needs to be copied over. Okay. The only other thing that we need to do for our frequency analysis is in the properties of the study. So right-click on the property, the study name, and go to properties. We just need to tell the software how many natural frequencies that we want it to calculate. Because technically there's an infinite number of natural frequencies for a structure, but in reality or in a practical sense, it's only the first few, 5 or 10, that really have a chance of being excited. Okay? So in this case, we're going to get the first 10 natural frequencies. Once we run the analysis, first thing we're going to do is go ahead and get a report of those 10. Okay? So in this case, the first 10 natural frequencies are in a range of, just under 11 hertz up to 35 hertz. Okay? So in this case, we're talking about an engine, so that corresponds with an engine speed of 650 RPM to 2100 RPM. Okay? So because this is a diesel engine, it's going to be a fairly low RPM. That means the entire operating range, or I should say the first 10 natural frequencies all occur within that operating range of the engine. Okay? The chances are, whatever speed we choose, we're going to be causing some kind of vibration. Okay? So besides the natural frequency, what we also get is what does the mode shape look like. Okay? So each natural frequency has a shape that it's going to vibrate. So our first natural frequency is kind of a top of the structure moving along the z-axis. Okay. So that corresponded to about 11 hertz or 650 RPM. So if we were running the engine RPM or kind of an idle, that's what the structure would be shaking like. Okay. On our second natural frequency, it's kind of a plus and minus of that back side along the x-axis. Okay, so that was a little bit over 11 hertz. So whatever speed that corresponds with, that structure would vibrate. Okay, so you can work your way down through. In this case, we have a total of 10 modes that we calculated. So you work your way down through the list and get an idea of how it would deform. Okay, that animation like that is also a really good way of looking to see where you might need to add some more corner braces or gussets or that kind of thing. Okay, now that we know what frequencies, what are our natural frequencies, we want to find out what kind of damage is going to happen if those natural frequencies get excited. Okay, so for harmonic analysis, and it is similar to the setup is identical to a linear static. Okay, the only difference is we're only putting the loading that's going to be oscillating. So in this case, it's the engine load and it's the pump load, but it's not the fuel tank. Okay, and we tell the software, I want to look between 10 and 25 hertz. Okay, so in our case, that's our operating range of the engine. And what we end up with is several plots that we can either look at frequency by frequency, or we've got a nice way where we can have it gather up instead of each frequency. We can have it take all of the frequencies, add it together, find the maximum that occurs. Okay? So in this case, we find out that the maximum displacement on the structure is due to the vibration is 6/1000 of an inch. Okay? What we don't know is what frequency or what engine speed that happens on. So we can probe that area of the model, and then we can get the response. Okay, let me get that plot. So in this case, it turns out that that maximum displacement occurs at the lowest natural frequency, so 10 hertz or 650 RPM. So in this case, it's going to show that no matter what speed it does vibrate, but the best choice would be 25 hertz, okay, or the highest engine speed. Okay. So that is stress, natural frequency, and vibration analysis. Okay. Now the next example we're going to look at is a very similar welded structure. Difference being is this one does not get lifted by a forklift, but it gets lifted into place with a crane. So we've got pad eyes and slings. Okay. Certainly there's a couple of ways that you can do it. One would be to actually model the slings as some metal rods and apply your load up there. Okay. What I've done differently on this one is I just use some sketch lines to represent the sling, and that's going to dictate the direction of my force. Okay. Now, because I'm pulling up on the pad eyes with what would be the weight of the equipment, instead of loading the structure, I'm going to restrain it. Okay. Let's start with that restraint. Okay. So wherever the equipment is, that now becomes a restraint. So in this case, these two rectangular channels, or C-channel, is what the equipment's loaded on. So I'm going to restrain the 4 joints. Okay. And then when I create the load, starting on this pad I first, for the selected direction in that line. Okay. So what it's going to do is it's going to be 5,000 pounds on that eyelet of the pad eye, but it's in the direction of that sketch. So it is up and to the center. Okay. So if we wanted to test shorter or longer slings, which would change the angle of the force, all we have to do is adjust that sketch. Okay. Everything else is the exact same setup as we did before. Okay. Now this one is a little bit different than the last analysis because it's a mix of solid elements and beam elements. Okay. So because we have 2 different stress types available, you cannot look at solids and beams together. Okay, so this is the stress in the solids, which are the pad eyes and the gussets. Okay, so we're looking at a von Mises stress of about 25 KSI. This one's an alloy steel, so that's a 90 KSI yield. So we're looking at kind of a 4x factor of safety. If we looked at the beams, we have that same stress available. Okay. One other thing that beams have is we can create a beam diagram. Okay. So maybe we wanted to create a shear or moment diagram of, we're just going to pick that top one, go ahead and give us the moment. Okay. So there's our moment diagram for the beam. Okay. We could do the same thing where we set direction 1, we could do direction 2. Instead of moment, if we wanted to show shear, okay. So again, that kind of corresponds to hand calculations. Okay. So the last thing we're going to look at is how we might do a detailed analysis for welds. Okay. There's kind of 2 ways that we could do a weld analysis. Okay. One is we have something in simulation specifically called an edge weld. Okay. Currently, the limitation is edge welds can only be used for surfaces, which creates shells or sheet metal parts. Okay. So if you wanted to do a weld analysis on a solid, you have to actually weld, or you have to model in the weld bead and then bond that to the shells. Okay. So I took this and made a surface model in SOLIDWORKS. Okay. So when you're defining your edge weld, you define the 2 faces that you want connected or welded together. And it will attempt to find the intersecting edge automatically. If it can't automatically, you just pick where you want the weld to be. Okay? You choose whether it's a single-sided or double-sided fillet or a single-sided or double-sided groove. Okay? When it does the factor of safety calculation, you decide whether you want to use the American standard or the European standard. You decide what electrode that you're using, and you give it the factor of safety, which defaults to 3 for the American standard, and then you tell it the weld bead size that you want to use. Okay, so it kind of works like a very sophisticated bonded contact at that point. Okay, so I fixed the top edge of that beam, and I've added 500 pounds to the edge of that beam. Okay, so we still get our normal stress plots. Okay, but what we also get is a weld check plot. Okay, so it goes bead by bead, and in this case we had 8 beads, and all of them are okay. Okay, it even goes a step further, and if we look at bead by bead, it tells us the size that it would need to be. So we had 0.375 on all of our beads, but this one in the front could have been smaller. Could have been 0.24. Around the corner, that one is pretty close. It needs to be 0.345. On that side, 0.281. On that fillet, 0.29. This back one, 0.07, so it doesn't carry really any load at all. This corner, 0.27, 0.28, 0.34. Okay, so if we wanted to keep it a uniform size all the way around, we're pretty much right on. You know, we could go down to 0.35 instead of 0.375. Okay, but our first guess was pretty close. Now, if it had failed, it would have done the same thing and told us the size of weld that we needed to increase it to. So that's how we go through and do a detailed weld analysis on a single joint. We've looked at stress and vibration. We've looked at how we can handle lifting with slings, and then we've looked at detailed weld analysis.
This has been Corey Bauer with GoEngineer. Thanks for watching this webinar.